So we're now going to talk a little bit about the connection between differentiability and continuity. So, and in particular, we're not going to prove, but we're going to help you start a proof of the statement that if f is differentiable at x, then f is continuous at x. So you can say that differentiability is a stronger property than continuity. So if we're talking about differentiability and continuity at a fixed point, then so you can say f differentiable at x, these guys form a smaller set than the guys that are continuous at x. So all the guys that are differentiable at x are also continuous at x, but the guys that are continuous at x, they form a bigger set than the guys that are differentiable there. A typical example would be the absolute value function. He's continuous at 0, but he's not differentiable at 0. So he would be here, okay? But let's say y is equal to x squared. He's both continuous and differentiable at 0. So he's a guy who belongs to that place. So how do we prove this? So let me give you just a sketch or the important players here. So well, it's the definition of what this means, and it's the definition of what this means. So our assumption is that f is differentiable at x. So this means that if you take the limit as h goes to 0 of f of x plus h minus f of x divided by h, this limit exists and is equal to this. And in this proof here, exactly what is equal to is not so important. The important thing is that this limit exists. And we want to prove what? Well, we want to prove that the limit as, let's say, x1 tends to x of f of x1, then this is equal to f of x. That's what we want to prove. And here, an important observation is that this can be written as lim x1 goes to x of f of x1 minus f of x is equal to 0. So proving this is the same as proving this. So how to connect the two? Well, observation here is also that we want a chain here of equalities connecting these two things. And the crucial thing to use is the fact that this limit exists. And now we can notice that by a change of variables, you can write this out as x1 tends to x of f of x1 minus f of x divided by x1 minus x. So writing the definition of the limit in this form or in this form is completely equivalent. You can see this by using the change of variables formula for the limit, or you can do this, as we have discussed in a different film, by just, for instance, if you're looking at the derivative of this function here at, let's say, this point, then what you need to do here is take your x, and then, well, usually we call this x plus h, and then you take the difference in height divided by the difference in the x direction, which gives you exactly this. Or you could give these points different names. Why call this x plus h? Why not call this one x1? So if you now do the difference in the height direction divided by the difference in the length direction, you're getting exactly this. So these two things are describing the same, you could say, phenomenon. And now this thing sure looks a little bit like this thing. So then the point is how to smuggle in something so that this appears here, and then how to deduce that whatever this gives is 0. So that's your job. So good luck.